Good evening, everyone. Good evening, everyone. Now, the next session will be taken by Professor Susavan Samanta, NIT Rourkela. It's my pleasure to introduce Professor Susavan Samanta. Professor Samanta received the ME degree from Jadavpur University, Kolkata, India in 2003 and the PhD degree from the Indian Institute of Technology, Kharagpur, India in 2012, both in electrical engineering. He is currently an associate professor with the Department of Electrical Engineering, NIT Rourkela. His research interests include analysis, modeling, and control of power converters used in photovoltaics, electric vehicles, and space application. Over to you, sir.
Yeah, thank you. So, what we will do in this session is, I think if you remember the last session, Professor Kapat from IIT Kharagpur was saying about different converter, which is basically now widely used in different applications. So, in this session, obviously the time is very less, but what I will do is I will try to design a boost converter for certain application. Like it is not only designing the power stage as well as the controller design that I will do, and my student will also show you the simulation results. So anyone is having the MATLAB, they can open their MATLAB simulating toolbox and start designing with us also. And so at the end of the day, I hope that you will be able to learn how to design a converter, a closed loop converter. So the specification that we have chosen to design is input voltage is 48 volt. Output voltage is 96 volt. The power level that we have chosen is it's 2 kilowatt. Sorry. Okay, so keeping in mind that in general, if you see the EVs like which is used in e-rickshaw and the scooty, nowadays they are using 48 volt battery. They're using 48 volt battery, but if you use the 48 volt battery and if और number में connect so if you use 48 volt battery directly to the inverter, then for a 2 kilowatt power level, you will have mostly how much is the current. So the battery current that will be drawing is 2000 divided by 48. So which is like a huge current. So you have to, your battery should be designed in that manner. But you can also use another option. You can use the same 48 volt battery, but then your DC link voltage will be 96. So the battery, the current that will draw from the battery will be obviously, it will be reduced to half, whatever it was from drawing from 48 volt. So this is almost the specification that we have chosen is kind of application on that, keeping in mind that application. And so this is the normal boost converter topology. So I have not considered here the different parasitics. You can consider the different parasitics. Now the first thing that you have to design for this converter is how to choose the power stage component, like the two filtering component, L and the C. Okay. This is first thing, and you know that this as the switches are there in the circuit, this is not a linear circuit. So it is a non-linear circuit because the switch is present in the circuit. So if I want to use the linear controller, so we need to linearize this non-linear system, and then only we can be able to apply the linear controller. And today's example, I will use this average current mode control technique, which is mostly used in boost converter application. So what is average current mode control? In the average current mode control, we are sensing the output voltage using the feedback resistance divider circuit, and then we are comparing this with your reference voltage. So this is basically your V feedback, this point, which is nothing but your R2 by R1 plus R2 into V0. So the error signal, it will pass through a PI controller, and then it will generate the, actually this ACMC is a two loop controller. So there is an outer loop, which is a voltage loop, which is slower, and there is an inner loop, which is a current loop, which is faster. So I can sense the inductor current, which is your IL, and this will give your IREF. So this is plus, this is minus. Then it will again, the inner loop also passing through a PI controller. Then this is the control signal. So till now we have a continuous signal, but we need to generate the pulse signal to drive the switch. So we need to use some modulation technique. So what we are doing is we are comparing with a comparator this signal with a ramp signal. Okay, and this output that we will get is basically a pulse signal, and then we can use a driver just to step up the voltage level and any delay or anything we want. So what I will do is that I will erase this portion now. So now I will connect Okay, so this is your driver. So this is the two loop system where we have a outer voltage loop and the inner current loop. I will draw the corresponding block diagram later on. But so now the objective is we need to find out the value of LC, the power stage. We need to find out the values of this outer loop PI controller and the inner loop PI controller. Okay. And to design the controller, because this is a linear controller, these two, so you need to find out the corresponding transfer function. Now, what transfer function? I think all of you know that ultimately this is your control input, this D, and this is the output you want to control. Okay. Now this D is basically generated from IL, and the I reference is generated from the outer loop. So the transfer functions that we require is basically IL by D for inner loop controller and V0 by IL for the outer loop PI controller. So that I will discuss when we will design the controller. So this is the ACMC control, average current mode control technique. Okay. So how to choose this L and C? L and C you can choose depending on your ripple specification. There are this is. Okay. So we have chosen, this is your IL, this is your VC. The ripple specification we have chosen delta IL, we have chosen as 20% of the output current, and the ripple specification for the capacitor we have chosen as much 2%, no? 2% of V0. Okay. So let us first draw the two waveform IL and VC, then you can understand that how you can get the L and C value from this ripple specification. Another assumptions that we are doing is that we are assuming that this converter is operating in continuous conduction mode. Okay. So what is the meaning of continuous conduction mode? Continuous conduction mode means the inductor current never becomes zero in a switching cycle. Okay. So if I draw the inductor current in steady state, and then what will be the corresponding IC and what will be the corresponding VC. Okay. So the switch is on, you can understand when the switch is on, the inductor is charging with the input voltage, and this diode is blocked by the output voltage. So when the during on time, inductor is charged through input voltage and the output load current is provided by the capacitor. Okay. So this is your on time, where inductor is charging, because all of us we know that the relationship is VL is equal to L DIL by dt, and during on time this VL is nothing but your input voltage. Okay, so the slope of the current waveform is V in by L. So this slope is V in by L, and the ripple current means the peak to peak current. So maximum to the minimum. So this is your ripple current. So delta IL, I can write delta IL is nothing but your slope into the corresponding time. So your slope is V in by L, and the corresponding time on time is D into T. So this is your D into T. And delta IL, we are already considered that it is nothing but your 20% of I naught. Okay, where is my phone? 20% of I naught. So now if you see in this expression, D, you know that for a boost converter, what is the D is, what is your output voltage and input voltage relationship is V in by 1 minus D. Actually, that you can able to, for any converter, you can able to find out the input output voltage relationship by either volt second balance, inductor volt second balance, or capacitor charge balance. So considering that you know that thing and you know the relationship of input output voltage of the boost converter. So as we know, already decided that V0 is 96 volt, V in is 48 volt, so your D will be 0.5. And the switching frequency that we have considered here is, what is Fs that we have considered? 20 kilohertz, okay. So the Fs switching frequency that we have considered is 20 kilohertz. Because actually we have designed one converter, boost converter in our lab with the IGBT. So IGBT has the maximum switching frequency of 25 kilohertz. So that is why we have used 20 kilohertz switching frequency here. But if you use MOSFET, then obviously you can increase the switching frequency. And as you know that if you increase the switching frequency, you can lower the inductor and filter size will be reduced. Okay. So, so you know TS, because this is nothing but your 1 by Fs. You know duty ratio, which is 0.5. You know input voltage. You know output current, because output power you know, output voltage you know. So now from this you can find out the value of L by this expression. And what is the L that we have calculated? We have calculated 287.63 microhenry. 287.63 microhenry. And in our design that we will show, we have actually, obviously, you cannot exactly get this value. So we have simulated with a greater than this value, and we have chosen 300 microhenry inductor for simulation. Obviously, if you choose more greater than this value, your ripple will be even smaller. So it will be smaller than the 20% value. Now, so this is the L value. Now, how to find out the capacitor value such that it will satisfy the ripple specification in the capacitor. So if you draw the capacitor current, now obviously during the on time, capacitor is totally providing the load current I0. And if you use the KCL, so IC equal to your minus I naught. So during on time, it is this current is minus, this current is I naught. And during off time, this capacitor current obviously will follow the inductor of time current. So this will be your capacitor current. Now how to get the waveform of VC? So we need to use the voltage current relationship of capacitor, which is IC is equal to C dVC by dt. Okay. And you can find out the VC. So your dVC is 1 by C IC dt. So VC, so if I integrate this, 1 by C is constant, so your VC now you can understand if the IC during on time IC is constant. So if you integrate, it will follow linearly. So during on time, the capacitor will discharge linearly. So during on time, capacitor will discharge linearly. And during off time, obviously the current is varying linearly. So you will get a parabolic relationship, but as the time is very short, you will again see kind of a linear behavior. Okay. So your voltage ripple is again nothing but your max peak to peak value. So this is your delta VC. Now, if I want to find out delta VC, so what is happening is that during on time, the capacitor is totally discharging, and during off time, capacitor is charging. So we know the relationship Q, the charge that is stored or discharged through the capacitor, is C into V. So Q is equal to CV relationship, we all know. So how much charge is discharged from the capacitor during on time is nothing but the area under this curve, which is your I0 into dTs. This is the amount that is discharged from the capacitor during on time, which is nothing but equal to your C into the voltage variation across the capacitor delta VC. So you can find out the value of C, which is nothing but your I0 into dTs divided by delta VC. So delta VC already you know from your ripple specification. So I0 you know, D you know, TS you know, delta VC you know. So you can find out the value of capacitor, which is 271 microfarad. But you also know that it is not possible to get that exact value because capacitors, when you go to the market, they have some specific value. So accordingly, we have chosen the capacitor value greater than this value, which is 470 microfarad. 470 microfarad. So we have chosen 470 microfarad for our simulation. So L value that we have chosen is 300 microhenry. C value that we have chosen is 470 microfarad. And input voltage is 48 volt. Output voltage is 96 volt. Output power is 2 kilowatt. What is the corresponding value of the resistance? 20? 4.6. Okay. So this value of R is 4.6 ohm. So now, before going to design the controller, let us, in the Simulink, what I will show right now is that we will produce a 50% duty cycle, and it is already developed this converter, and we will show that these values is actually satisfying your ripple specification. So can you just, okay, hold on, let me, okay, can you open your Simulink blocks? Open loop, yeah. Already it is open now. Now see, open this one. It's opening, okay. Hmm. Hmm. Acha, okay. It is, yeah. Okay. And no, just 1 minute, just open one. So see, obviously inductor, nothing is ideal in the life. So inductor, when we are designing the inductor, we are using a core and then the copper wire to wound the core. So obviously it has some that winding certain resistance. So you can consider a, oh, there also it is changing. Okay. So you can consider the corresponding some, we have considered some RL value, inductor resistance. Similarly, the capacitor is also, it's not ideal. So capacitor, when you are representing the loss element of the capacitor, we are saying it is a equivalent series resistance. So this representing the ESR of capacitor. Now can you simulate? It is 48 volt. Output should be D is 0.5. Where is the D? And the D that was gone, I think. Can you check your simulation file? Oh, okay, it is there. So Yeah, so it is 20 kilowatts. It is 50%, so 0.5. And can you show the L values and C values, corresponding L values and C values? L values is 300 microhenry, that is already we have said. Can you show the capacitor value? It is 470 microfarad. Now can you just do the simulation and check the voltage and the current waveform? Clear all. Just not all, huh? You can reduce the time, no? Then it is already reached the steady state. Uh, uh, no, no. A little bit more, at least show me 510. No, 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 not now. Five another. Okay, okay. But the voltage waveform is not too good. Okay, okay. ठीक है. Okay. Okay. Now you can understand. Okay, okay. It is okay. So as I said that this is your what is the peak to peak value? Can you peak to peak value is 3.53 ampere. And if you remember your output, what was our output voltage? Sorry, output current. Output current is 20 point. V0 is your 96 volt, and your R0 is 4.6. So I0 is coming to be around 20.6 ampere. So 20% of that, so it will be more than 4 ampere. As we are using more than the L value, so we are getting, obviously, so it is satisfying my ripple criteria. Similarly, you can check the delta VC also, get the output ripple, and it is also satisfying. Another point I want to mention is that as you see the inductor current is increasing, so this is during on time, the capacitor is totally providing the load, so that is why capacitor is discharging. So this is the linear variation. Obviously, this is not exactly linear, but at the time is very short, so you are getting almost kind of a linear waveform, but actually it is a parabolic. It is obviously from the relationship you can understand it should be kind of a parabolic, but the time scale is so small that you are getting linear. So this is your discharging of the capacitor this time on time and charging capacitor in the off time. So this is regarding the so now you can stop your simulation. Okay. Okay. So uh, now next job is to find out this controller value, two controller value, two PI's value. So for that, as I said, we need to do the uh, we need to find out the different transfer function. Okay. So there are different techniques to find out the transfer function. We have used here the state space averaging technique. Uh, Okay, okay, okay. I can get that one also, na? Okay. So we will use the state space averaging technique. We have used the state space averaging technique to find out the transfer function. So state space averaging, obviously I will not go through the state space averaging technique because it will take more time. So there are 3 steps in state space averaging technique. One is that you have to write down the circuit equation in state space form during on time and off time. Then you need to do the time averaged, and after time average it will be a nonlinear equation, and from the nonlinear equation, to get the linear model from the nonlinear equation, you need to do some linearization technique. Okay, so by that way you can find out the different transfer function. Now if I try to draw the block diagram of the circuit diagram that I have already used for average current mode control, then my output was V0. Okay, and so I need to always regulate the output voltage. So the output voltage, I am sensing the output voltage. So there is a sensor gain which I am considering as kV. That is nothing but your resistance divider circuit gain. Now this one I am comparing with a reference voltage okay. You just check the, I'm drawing this block diagram from the circuit diagram that we have already drawn in the previous page. So then the error will generate, and this error we are passing through the PI controller to generate the inner loop reference signal, which is IREF. Now this IREF I'm comparing with the actual inductor current. Okay. And then this error is passing through the PI controller. And then we are using some modulation technique. And if you find out the linear model of the PWM technique, it is basically 1 by Vm, where the Vm is peak to peak value of the sawtooth waveform. So this is your 1 by Vm. Then we are getting the duty ratio. Okay, and from that duty ratio, I need to get the IL. So how do I get the IL? So there will be a transfer function where the input is the duty ratio. From the circuit diagram also you can understand the output is your inductor current. So that inductor current, now again you can use some sensor here, because sensor, if you use, either you can use a Hall sensor or simple sense register, but all has having some gain. So you can have the sensor gain. Okay. So this is, so what is the output is IL and the input is duty ratio. So you need to find out the transfer function between inductor current to duty ratio, which I am now mentioning as GILD. Okay. So that means it is the transfer function between inductor current to duty ratio. GIL then D. Now, so you need to have a transfer function to get the V0. You need to have a transfer function between inductor current and the output voltage. So this is nothing but your GIL and V0. So we need to find out this transfer function GILD. We need to find out the transfer function GILV0. KV already we can able to find out depending on your output voltage and depending on your V reference. So if you use here we are using 96 volt and the V reference that we are using is 2.3 volt. So you understand what will be the KV. Okay. So obviously it should be 3 by 96. Similarly, depending on the sensor, we have a sensor gain. So how much sensor gain we are considering here? 1 by 10. 1 by 10. VM, we are considering 1 volt. So this is basically a kind of a unit you can consider. So there is whether you can consider that block or not consider that block, it will not affect anything. So now we need to get the transfer function between inductor current to duty ratio and output voltage to inductor. So using state space averaging technique, you can find out this GV0D, which is the transfer function between output voltage and the duty ratio. Sorry, I should not write S as this one. So it is V0 S and by ds, this is nothing but your transfer function between V0 to D, and also you can find out the transfer function GILD, which is nothing but between inductor current and the duty ratio. It is available in the book. Many books it is available. It is also easy, but today it's not, time is not there. It is only just the state space equation that you have to write down. Then you have to find out the average model of the state space to on-time circuit and off-time circuit, and from there you can do the linearization. You will get the these two. And how to get the V0 GV0 IL? You can simply divide this transfer function GV0D and GILD. So this is nothing but V0 to IL is nothing but your GV0 okay, and boost converter as inherently as a right up plane zero. So the controlling boost converter is difficult than the buck converter because of the right up plane zero that is there. And you can understand the right up plane zero is nothing but actually it creates a delay. And why the delay is coming, that you can understand from the operation of the boost converter. Okay. So there is a right up plane zero. So next what we will do is we have already found out this 3 transfer function. Actually we don't, for our case, to design this PI controller outer loop, we need to find out this transfer function GV0 and IL. And for inner loop controller, current controller, we need to know this GILD. So I will show first GILD, okay, and then we will design the PI controller. After that, we will take this outer loop transfer function GV0YL to design the PI controller, and then we will show you the closed loop simulation results. First, can you show the okay? And here also we are considering the parasitics. You can understand this is basically initially I told my student to there is in MATLAB there is one toolbox, symbolic toolbox is there. So if you use the symbolic toolbox, you can actually find out the transfer function in terms of RLC, not in numerical values. Okay. So can you just first show the, are you showing the symbolic values? Okay. And the corresponding transfer function is here, no? Where it is? This is the corresponding transfer function. Okay. Have you used the pretty command? Okay. So this is basically the transfer function between IL and D. Now can you plot the Bode plot of uncompensated system or only IL, GILD? No. Okay. So this is GILD. Now, what is the loop gain? Okay, just 1 minute. I need to where I am. Okay, I need to. Oh, yeah. So see, so this one I will say as CI, controller for inner loop. Okay. So this is nothing but your KP 1 plus KI1 by S. So the loop gain, inner loop gain, this loop gain is multiplication of all the blocks. So it is nothing but your CI S. The PWM block has a gain of 1, so no point. Then GILDS into KES. So we have already seen the GILDS. To design the controller, we need to multiply with the gain also. So now we are plotting this multiplied with the sensor gain. Can you plot that one? Because then only we can able to design the controller. Okay. Obviously, you can understand that as the it is a so gain will reduced now, and as the gain is reduced, so what is the bandwidth of this uncompensated system? We can understand the bandwidth as what the power electronics is concerned. Bandwidth is where the magnitude plot crosses 0 dB. Okay. So magnitude plot crosses 0 dB around this point. So this is your 1 kilohertz. Okay. Just can you just make this mic? Okay, so you can use the tool, na, stability tool. You can use the stability tool. You can get the mark. All stability margin. Make all stability margin. Yeah. So you can see that the uncompensated system has the phase margin, because it's 90. So minus 180 is your rate line. So there is almost 90-degree phase margin is there, and uh, the bandwidth is uncompensated system bandwidth is 5 kilohertz, approximately 5 kilohertz. And we want to design the PI controller. Now we want to design the inner loop PI controller. There are, see, now another point is that there are various techniques that you can use to design the PI controller, because it is only the tuning method. Different tuning methods are available to find out this KP1 and KI1, the inner loop. What we have used is basically we are trying to use the information of we have chosen the closed loop bandwidth and phase margin specification to find out the inner loop controller. Okay, inner loop controller gain, the PI gains. So uncompensated, we have already seen the uncompensated system has the bandwidth of 5 kilohertz approximately, and with a phase margin of 90 degree, almost 90 degree. Okay. Now we want to design a PI controller such that the closed loop system is having a bandwidth of 2 kilohertz. Inner loop bandwidth, the closed loop bandwidth should be 2 kilohertz. And what is the phase margin that we have chosen? 60 degree. 60 degree. Okay. So now the problem becomes, so this is your inner loop gain. So Ti, this is your KP1, KI1 into this this is KI, the sensor gain, inner loop sensor gain. Now at the closed loop, so this is your closed loop bandwidth specification. So closed loop bandwidth specification means if I now wanted to evaluate this function at bandwidth, closed loop bandwidth at 2 kilohertz, which is your closed loop bandwidth. Okay. Then at bandwidth, as we have already seen, the bandwidth, the definition of bandwidth is where the magnitude plot crosses 0 dB. So that means what we want in the inner loop to design the controller such that so at 2 kilohertz, it is crossing 0 dB. So that means in linear scale, the magnitude is 1 and the angle is the phase margin that should be there. Now this is a constant. This sensor gain is constant, and this GILDS is a transfer function which is in the form I can it's somewhat lengthy, but so it is V in C into R divided by 1 minus D into S plus 2 by RC. This is the numerator, and the denominator is 1 plus SL R into 1 minus D whole square plus SS square LC by 1 minus D whole square. So this is your GILDS. So now I want to evaluate at 2 kilohertz. That means S I have to replace with J omega, or rather J into omega is equal to your 2 pi f. So I can write down 2 pi f, and this f is 2 kilohertz. So I can evaluate this whole function at 2 kilohertz, where all the parameters are known, because you know V in, you know C, you know R, you know D, everything is known. And if I evaluate at 2 kilohertz from this function, I will get some real part and imaginary part. Similarly, if I evaluate this, I will get a real part and imaginary part. Now, in the right hand side, you have a real part, which will be, there will be some relationship in the real part of Kp1 and Ki1. Similarly, if I have real, so this one will have real part plus the imaginary part. And in the real part, we have a Kp1, Ki1. In the imaginary part, we have also Kp1, Ki1. Similarly, in the left hand side also we can make this function as real part plus imaginary part. We can now equate the real part from the left hand side to the right hand side, the imaginary part from the left hand side to the right hand side, and we can get two, because we have two unknown, we will get two equations. So if I solve, then we will get the Kp1 and Ki1. So this is one of the methods. This is not the only method. There are other methods also, where by using those methods you can use the find out the the PI controller value. So we did this, and what values we got? Correspondingly, Kp1 and the Ki1. What value we got? Have you written here? No. So one is 0.1753 and Kp is 0.1753 and Ki is 618.8239. So this is the inner loop values. Okay. Now, so similarly, so if I see the loop gain in the outer loop, so what's the loop gain in the outer loop? So either you can consider, because now this block, everything you know, because you have already designed. Okay, so you know what is the relationship of IL by IL ref. And using the, it is nothing but your forward gain divided by you. It is obviously, you know, this transfer function is GS by 1 plus GSHS. Okay. Now, if you think that your loop gain, like GS into HS, is much greater than 1, which is in all practical case that is happening. So this IL by IL ref is nothing but your the transfer function will become 1 by HS, which is nothing but, so this one actually you can replace by 1 by Ki only. This total block. Okay. So this total block, either you can see, either you can do the approximation, otherwise you can use this total thing here. No problem. But everything you know with this transfer function because you know the Pi value now. Now what is the outer loop gain? Outer loop gain is obviously this total thing, which I can make what I can make this. So this one I can consider some as P of S. So this TV, the outer loop gain is now, this is your outer loop PI controller. So CV of S into this P of S into GIL V0S into your KV. So this is your outer loop again. Now this PS, as I said, this PS I can, for all practical purpose, you can actually replace with 1 by Ki. Then this is GL V0S into KV. So now here again you see that KV is a constant, Ki is a constant, GIL V0S is your transfer function between D0 and IL. Already we know V0 by D transfer function, we know IL by D transfer function, so we will get this transfer function. So the only unknown parameter is the outer loop PI controller. So that is basically your KP2 plus KI2 by S into KV into divided by KI into your GIL V0S. Okay, this is your outer loop gain. So in the same way as we did last time, again we can specify the outer loop bandwidth and the phase margin. Okay. Now there is one point. The point that I want to make here is this V0 by D, as already told, it has a right of plane 0. And you can understand the denominator of both these transfer function will actually cancel when we are finding out V0 IL. So we will only get the numerator of the transfer function, which is having a right of plane 0, and numerator of the current transfer function. So if you see, this transfer function is, which one? No, this is not. So division of this one. Okay. Okay. So this will be like V0 by 1 minus D into 1 minus S by omega Z, where omega Z is depends on L, R, and D dash. And in the denominator, we are having V in C R divided by 1 minus D S plus 2 by RC. This is basically, as I said, this is nothing but, if you see carefully, this is the numerator of IL by D transfer function, and this is the numerator of V0 by D transfer function, because the denominator will be the same and they will be cancelling each other while try to finding out this transfer function. So to find out So in general, the rule is because this right of plane 0 is there. So the bandwidth, outer loop bandwidth that we have chosen, the bandwidth, outer loop bandwidth that we have chosen is basically omega z by 6. Okay. And our omega z was approximately, how much was the omega z? This is basically, but what is the numerical value? Around 540, around approximately 560 hertz. Okay. So you can, so it is how much? Uh, 90 hertz. More than 90. So you can approximate is, you can say approximately it is 100 hertz. So 2 kilohertz was the inner loop bandwidth that we have designed with the 60-degree phase margin. Outer loop bandwidth we are designed for 100 hertz, and the bandwidth is same 60 degree phase margin 60 degree. Okay. So these are the two specifications that we have chosen for the outer loop, 100 hertz and 60 degree. Now if you come, it is exactly the same way. So this TVS is now basically 1 and it is 60 degree, and we are evaluating this total function at 100 hertz. So again, if we evaluate, we'll have a real part, we have an imaginary part which is containing Kp2 and Ki2. So we have two equation, two unknown. We can find out the Kp2 and Ki2. As I am already said multiple times, this is one of the tuning rule that we have used by using the closed loop bandwidth and phase margin specification. But you can use your own rule and you can tune yourself. Okay. Now can you go to the closed loop? The final is closed loop simulation. We have did the closed loop simulation. Can you first show the? Okay. So let me explain first. So this is the, you can understand that this is the open loop block diagram, open loop circuit diagram that we have already showed to you previously. This is your R2 R1 just to get this 3 by 96. So because your V0 is 3 volt, the reference that we are given is 3 volt. Now, so this is V0. Now can you go to this inner loop block diagram, the ACMC block diagram? Okay. Now if you see, so this is your V0, this is approximately that feedback voltage. It's not basically the V0, it is the feedback voltage after the resistance divided circuit. Then we are comparing with the reference. So error, this error is passing through the PI, and obviously we are using some saturation block here. So this will give me what? Current reference value. So this is your current reference value. This current reference value is compared with your IL, and then we are having the inner loop PI. Inner loop PI is now, this is basically your modulator. So this is your sawtooth waveform. We are comparing with the sawtooth waveform where we are generating the duty ratio. That duty is, so this one we are giving directly to the, this G is directly giving to the switch here, the gate signal. Now can you simulate? And now another thing is this is the current sensor gain 2 by 20, that as I already mentioned, that is 1 by 10. Now can you show the closed loop simulation? Okay, so you want to, so two things. Okay, first let us show the block Bode plot, because we have already did the KPKI and we need to check that whether it is satisfying that. So first, can you show the GI uncompensated system and the compensated system? Okay, so we have multiple. So can you, okay, uh, uh, okay, okay. So you can understand obviously because of the PI gain, we have that because we have used the integrator. Integrator has that because it is integrating. Okay, so you have high gain at the low frequency. So this blue one is basically your uncompensated system, but it is without KI. If you multiply KI, then obviously it will be reduced that we have. And then this is the total compensated system. And compensated system, as we said, that we have uh, which one is the compens? So this is basically your compensated system. No, you have not multiplied by KI. It should be multiplied by KI. Otherwise, it is not. Just check because it is not 2 kilohertz. And yeah, that is what. Here also, no, you should multiply this one because this is your PI. No, this is the transfer function. This is HI. And where is your controller? GX? Huh? The GX for outer loop. So this is the inner loop controller. Okay, sorry. So this is your IL by D transfer function. 1 by Vm is unity. This is your sensor gain. It should be multiplied by the controller. So this is your loop gain. So now we can you plot this one? Okay. So this is, can you show the stability margin? Yeah. So previously it was, now it is not 2 kilohertz. We have designed for 2 kilohertz, no? And what is the phase margin that we are getting? Obviously 60 degree. Okay. So margin is okay, but we have reduced the bandwidth. As I said, this is basically very, it is not uh, exactly, it may not match because we may not consider the parasitics and other effect here in the controller design. Phase margin is, that is the most important thing is the phase margin, which is matching. So can you show me the outer loop design also? So which one is the compensated system? So this is the compensated system. We have designed for 100 hertz. Uh, we got around 100 hertz, and what is the phase margin? It is 60 degree. So phase margin is satisfied. Now can you show the Simulink block and go to the Simulink block and simulate the closed loop simulation? No, this is not closed loop. This is open loop, no? Oh, this is closed. Yeah. Have you given any load step? No. You have given load step. Okay. So what we want to see? No, not this one. We want to see the full output voltage. And we want to see the inductor current. So this is your output voltage. So we have designed for 96 volt. So we will see first the load step effect because we are designing the load the disturbance. How much current you have changed? 100%. So you have 20 ampere. So you're increasing to 40 ampere. Okay. Yeah. Okay. So this is your So you can see this is the 100% with 100 giving 100% load variation. This is the output voltage response, and can you show me the current response, inductor current? Yeah. So this is your current response. So you can understand from the response itself that why the current loop is faster than the voltage loop. Current loop obviously settles much faster than the voltage loop. So anyone is having any question? Okay. So I think we can finish it here today. You can later on also, if you have any problem with the simulation or any queries, you can later on you can email me or you can ask me. Okay. Thank you.
So it's the time to wind off. Thank you, Professor Samantha, for your informative session on boost converter modeling, design, and the Bode analysis. Tomorrow we'll start our session at 9:30. Thank you, everyone. Have a good day.